Hi everybody. So now it's the marriage of Figaro, and we are starting chapter 8, which is about proofs involving sets. And the fact is that a lot of the ideas behind logic transform pretty directly into statements about sets. They're very closely connected. We saw this earlier, and we'll see it in more detail now. So let's start at the very beginning with some of the simplest questions about membership in sets. So a lot of times theorems can be expressed as questions about the relationship between sets, and sometimes really just a statement about whether one thing belongs to another set. And actually the theorem that we spent so much time on in chapter 7, Euclid's algorithm, is exactly of this form. So let me remind you of the original formulation of Euclid's algorithm, or Euclid's theorem. That's this here. It says, for any natural numbers a and b, there exist integers k and l such that the greatest common divisor of a and b is ak plus bl. So written this way, the theorem is a statement about a solution of an equation. If you put the greatest common divisor on the left, you can find integers k and l that solve this equation. But we can write this a little bit differently, and in fact, if we write it a little bit differently, it's even closer to the way that we actually proved this result. So let's do it this way. Same theorem. Let a and b be natural numbers, and define the set big A to be the collection of pairs, a collection of numbers that are of the form ax plus by, where x and y are integers. Then the greatest common divisor of a and b belongs to the set A. So this is using set builder notation to express the same idea that we did in the statement of the theorem, because what we're saying is to say that the greatest common divisor of a and b belongs to the set A is to say that GCD of a and b is equal to ax plus by for some x, y in z. And that's the same statement as in the theorem. Let's look at maybe some simpler examples of the same idea. So the way this works generally is that you're given something in set builder notation, and that usually means you're told that x is an element of a set S with an additional property. Some property p of x is true. And I should maybe emphasize this x is a dummy variable. So another way to read this set builder notation is to say that x is an element of the set A if and only if it's an element of the set S and the property p of x holds. So here's a simple example. Let's let A be the collection of integers of the form 3x plus 2 as x runs over the integers. So these are the integers. I mean, let's write down a few of them. X could be minus 3, and so we would have, if x is minus 3 times 3 plus 2, that's minus 7. 3 times minus 2 plus 2, that's minus 4. 3 times minus 1 plus 2, that's minus 1. And if you look here, each of these things is going up by 3, because as you increase x, you add 3 to 3x plus 2. So the next one's going to be 2, and then 5, and then so on. So this is an example of an arithmetic progression. The numbers are all separated by 3. And the claim here is that 14 is an element of this set. So how do we decide if that's true or not? We need to know, is 14 equal to 3x plus 2 for some x in z? Because that's what it means. To belong to A is to be of the form 3x plus 2 for some x in z. And actually, if we look at this equation, we see that 12 is 3x, so x is 4. So the answer is yes, because 14 is 3 times 4 plus 2. On the other hand, 13 is not an element of A, because if you write 13 equals 3x plus 2, you get that x is 11 divided by 3, which is not in Z. And so even though, yes, 13 can be written in the form 3x plus 2, it can't be written in that form with the restriction that the x value has to be an integer. Here's another version of a slightly fancier way of writing the same thing, maybe a little more general. So again, the same set A is the set of things of the form 3x plus 2 as x runs through the integers. And the claim is that if x is congruent to 2 mod 3, then x is in A. So to interpret this, we have to remember what x congruent to 2 mod 3 means. It's always good to remember your definitions. So x congruent to 2 mod 3 means that x minus 2 is divisible by 3. That's the definition. In other words, x minus 2 is 3y for some integer y. But that means that x is equal to 3y plus 2 for some integer y. And that means that x is in A. Because to be in A, you have to be of the form 3 times an integer plus 2. Here's a slightly fancier example. You should look at there's some nice examples in the book, and of course you should definitely look at those. And this example is kind of based on one of the examples in the book, but it's a little bit fancier. So I didn't use set builder notation here because it didn't fit on the slide when I typeset it. But if I did want to use set builder notation, I would write this like this. B is equal to the set of x in, and remember what this is, it's the power set of the natural numbers. It's the collection of all subsets of the natural numbers, such that for all x and y in the set big X, absolute value of x minus y is less than 2. So when I tried to put this into the typesetting program, it was too long. So now my first question is the set minus 1, 2, is this in B? Well, the first requirement to belong to the set B is you have to be an element of the power set of the natural numbers. So the power set of the natural numbers is the collection of all subsets of n. Is minus 1 comma 2 a subset of the natural numbers? No, because minus 1 is not in the natural numbers. So to be a subset, you have to be included in the natural numbers, and you're not. So minus 1 comma 2 isn't in B because it doesn't meet the first requirement. It doesn't belong to the set that I was calling S up above, the sort of place the starting set, because it isn't in the natural numbers. So who cares whether this other condition is satisfied? It doesn't matter. What about the set 0, 1? I guess in my when I wrote these notes, I was being silly. Let's not use 0, 1 here. Let's use 2, 3. Is 2, 3 in the set? B? Well, now 2, 3 is in the power set because it's a subset of the natural numbers. Its elements are all natural numbers. So we have to check the second condition. is it true that for all x and y, the absolute value of x minus y is less than 2? Well, we have to pick x and y from this set. And there's 3 ways we can do that. Well, 4 really. Here's x and here's y. We can pick 2 both times. We can pick x to be 2 and y to be 3. We can pick y to be 3 and x to be 3 and y to be 2. And we can pick 3 both times. And if we look at the absolute value of x minus y in each case, it's 0, 1, 1, 0. All of which are less than 2. So the set 2, 3 is an element of B. Let's look at one more example. What about the set 1, 2, 3, 4? Is this in B? Well, it is a subset of the natural numbers. So it is an element of the power set of n. But if we look at the differences between elements of the set, so here there's a lot of possibilities, but just notice that the absolute value of 4 minus 1 is 3, which is bigger than 2. So 1, 2, 3, 4 does not have the property that absolute value x minus y is less than 2 for all x and y in X. So to decide if a subset belongs to this power set, you need to know, first of all, are all of its entries natural numbers? And second of all, is the largest distance between any 2 points in the subset less than 2? That's what this idea is getting across. Okay, so think about that, and do be sure to look carefully at this section in the book for some more examples.